All right, let's jump right into it. If you work in machine learning or data science, you know it is incredibly common to just treat matrices like black boxes, right? We feed a bunch of numbers in, we get some numbers out, and we kind of just cross our fingers and hope the math did its job. But in this explainer, we are completely changing that approach. We're going to stop looking at matrices as boring flat grids of numbers, and we're going to start seeing the visceral geometric reality of your data. We're talking about eigenvectors and eigenvalues, which, believe it or not, are the absolute structural foundations of almost everything we do in modern AI.
Picture this for a second. You're looking at a totally chaotic mess of, say, millions of machine learning parameters. At first glance, it looks like pure noise. But what if you could just strip all of that noise away? Because hidden inside almost every matrix are these perfectly stable, absolutely unshakable axes. They cut right through all the rotational chaos and expose the true skeleton of your data. By the end of this, you're going to know exactly how to find them, what they physically mean, and why they are basically a secret weapon for stabilizing your models.
Okay, Section 1. The chaos of matrices, stretching and rotating space.
Now, to understand this hidden skeleton, we really have to understand the chaos first. Normally, when you multiply a vector by a matrix, it gets thrown around. The matrix stretches it, sure, but it also rotates it into a completely new direction. But hidden inside that mess are special directions. While your normal everyday vectors get warped, eigenvectors stubbornly refuse to rotate. I mean, they literally will not do it. When you hit them with a matrix, they stay perfectly aligned on their original line. They only stretch or shrink. And fun fact, the term eigen actually comes from German, meaning own or characteristic, because these vectors intrinsically belong to that specific matrix. Moving on to Section 2, the rubber sheet analogy, a visceral geometric reality. To really get a gut-level feel for this, let's step away from the numbers entirely. Imagine a thick, heavy rubber sheet. It's got a grid drawn on it and a bunch of random arrows pointing in all directions, and it's pinned down securely at the edges. Now, I want you to imagine physically grabbing that sheet and just pulling it, stretching it hard left, right, up, down. As you pull, watch what happens to all those arrows. The stretching literally pulls them off their original path, right? It forces them to change where they're pointing. The stretch itself creates rotational warp.
But if you look really closely at that stretched rubber sheet, you'd notice something kind of incredible. A very specific, tiny handful of those arrows wouldn't tilt at all. They might get a lot longer, or maybe squished shorter, but they would still point exactly along the original line they started on. They completely and utterly resist the rotational warp. Those perfectly stubborn arrows on your rubber sheet, those are your eigenvectors. They are the natural, built-in axes of the stretch. And that brings us directly to eigenvalues. The eigenvalue is simply the exact amount that specific stubborn arrow stretched. So if the arrow doubled in length, your eigenvalue is 2. If it got completely flipped backward, but hey, it stayed on the same line, the eigenvalue is -1. Think of the matrix as this big chaotic blender. The eigenvectors are the unshakable axes that the blades spin on, and the eigenvalues, that's the speed those blades are actually spinning.
All right, Section 3, the defining equations, translating geometry into math.
So how do we actually find these unshakable axes in practice? Well, we have to write down this whole refusing to rotate idea mathematically. And that gives us our defining equation, a times x equals lambda times x. Let's break that down conversationally. Applying our chaotic matrix A to our special vector x gives us the exact same output as simply scaling that vector's length by a single number, lambda. The output is perfectly 100% parallel to the input. Let's walk through how this builds, step by step, because it's pretty elegant. To solve it, we just rearrange the equation, moving everything over to one side. Then, to factor things out cleanly, we introduce an identity matrix. Think of it like multiplying by 1. Now, ultimately, to find a real, actually useful vector and not just a boring 0, we have to find where the matrix completely collapses space. And that leads us to the final step, setting the determinant of that whole thing to 0. This is known as the characteristic equation, and solving it is exactly what unlocks those eigenvalues for us.
Once we actually have those values, we arrive at this genuinely beautiful result called eigendecomposition. Basically, it lets us completely deconstruct our totally chaotic matrix into 3 clean, perfectly logical steps. First, we rotate our space so everything lines up perfectly with our eigenvectors. Then, we stretch everything along those axes by the eigenvalues. And finally, we just rotate everything back. We have completely replaced chaos with a clean, understandable sequence.
Section 4. Shaping data with PCA. from circles to ellipses.
Let's look at how this actually shapes real-world data, specifically in principal component analysis, or PCA. We use these exact tools to figure out the shape of massive datasets. Picture a perfectly uniform cloud of data points, like a perfect unit circle spreading out equally in every direction. Now apply a covariance matrix to that data. What happens? That uniform circle morphs, it stretches, and it skews into an elongated ellipse, and that new shape is dictated entirely by the matrix.
This is where it gets super cool, because it brilliantly shows how eigenvalues determine the physical shape of our data. The major axis, literally the absolute longest diameter of that new data ellipse, is governed exactly by your largest eigenvalue. It points precisely to where your data is stretched the most. That's your maximum variance. On the flip side, the shortest diameter is your smallest eigenvalue. In PCA, those eigenvectors are your principal components, and the eigenvalues are literally telling you how thick or spread out your data cloud is along those specific axes.
Which brings us to Section 5, the DNA of AI, where eigenvectors live in machine learning.
So why do you, as an engineer or data scientist, absolutely need to care about this? Because treating a matrix as a black box traps you in a cycle of blind trial and error. Eigendecomposition is, quite frankly, the mathematical MRI of matrices. It is everywhere. We just saw it in PCA. But it's also powering spectral graph neural networks, defining the frequencies we use to filter out nodes. In GANs, it's the largest eigenvalue that actually prevents your models from completely collapsing. In Google's PageRank algorithm, the winning web pages are literally an eigenvector. And in modern diffusion models, eigenvalues are what dictate how we schedule noise.
But honestly, nowhere is this more high stakes than in optimization. Listen to this. The eigenvalues of the Hessian matrix dictate whether your model will train in 10 minutes or 10 grueling days. If the ratio between your largest and smallest eigenvalue is huge, your loss landscape is essentially shaped like a super deep, narrow canyon. Your optimizer is just going to zigzag hopelessly, bang against steep walls while crawling forward at an absolute snail's pace. The geometry of those eigenvectors fundamentally dictates your training time.
So getting this right in your code is absolutely crucial. Here is a rapid-fire engineering tip that might legitimately save you from tearing your hair out at 2 a.m. If you're working in PyTorch with symmetric matrices, things like covariances or Hessians, always use torch.linealg.eig with an H at the end, instead of just eig. Standard eig can actually spit out complex numbers because of weird floating point math, and it will crash your downstream operations. Adding that H exploits the symmetry, it absolutely guarantees real numbers, it automatically sorts your values, and honestly, it cuts your compute time in half. It is a real game changer.
So let's cement the mental model we've built in this explainer. Think of a matrix as a totally chaotic data blender. No matter how violently it mixes and stretches space, the eigenvectors are the unshakable structural beams bearing the load of that transformation. They never, ever rotate. And the eigenvectors? They are simply the stress gauges attached to those beams, measuring the exact amount of stretching force acting along them. Once you start seeing matrices this way, I promise you can't unsee it. They aren't just arbitrary grids of numbers anymore. They are geometric forces with clearly defined, totally stable axes. So I'll leave you with this thought. If eigenvectors are the true DNA of a matrix, what hidden structural axes are waiting to be discovered in your own data? It's time to stop relying on blind trial and error. Run the mathematical MRI and find the skeleton hiding inside your models. Thanks so much for joining me for this explainer, and keep exploring the geometry of your data.